Okay, thank you for the opportunity to give this talk. I will talk about subsystem decompositions of quantum circuits and processes with indefinite causal order. This is joint work with Julian Wechs and Julian Wechs. So first of all, I will give an outline or an overview of what I'm going to talk about. Our usual understanding of causality is that events are embedded into a definite causal order. So we have two events A and B. We have essentially three possibilities. Either A is in the past of B and can causally influence what happens at B, or B is in the past of A and can causally influence A, or if events do not causally influence each other. And in recent years, a question that has attracted a lot of interest in quantum information and quantum formations is whether what happens to causal relations when quantum theory comes into play, and can causal relations themselves be subject to quantum effects. And a particular framework that has been used to study quantum causal relations is the so-called process matrix formalism. In this formalism, one assumes local quantum operations, but one does not assume any a priori causal structure in which these operations are embedded. And one finds that there indeed exist scenarios that are not compatible with the definite causal order. The central open question in this whole line of research is whether this phenomenon of indefinite causal order is physically realizable in some way. And some processes with indefinite causal order are believed to have a physical realization within standard quantum theory. It's a controversial question, and there's a debate about whether these kind of situations are indeed genuine realizations or simulations of processes with indefinite causal order. So if one wants to say that one can indeed realize indefinite causal order in standard quantum theory, one should clarify in which precise sense such situations are realizations of processes with indefinite causal order. And the precise sense to say that is that certain causally indefinite processes can take place as standard quantum mechanical evolutions, so described by acyclic quantum circuits, if these circuits are described with respect to an alternative choice of quantum subsystems which can be delocalized in time. Or in other words, one can convert between the standard quantum description of the situations in terms of some acyclic quantum circuit and the description in the process matrix framework by performing a change of subsystems. So this has first been shown by Julian Wechs in this paper from 2019, and then being further developed paper from earlier this year, and some ongoing work. And in this talk, I want to explain this idea in a very general way, so to present a general framework of what it means to describe a certain quantum circuit with respect to different choices of subsystems, and then to show how this applies to processes with indefinite causal order. So here's a more detailed outline. I will first present briefly this process matrix framework, so this abstract framework which we use to study causal relations in quantum theory. Then I will present this general framework of subsystem decompositions of quantum circuits. Then I will show how it applies to certain processes with indefinite causal order. And then I will give some outlook and discussion, in particular about the question whether one can transform between causal perspectives in the quantum switch. So let's first look into this abstract process matrix framework. And the starting point of this framework is that one assumes separate parties that reside in local laboratories. So they are called Alice and Bob. And these parties' actions are described by quantum theory. So they have some incoming and outgoing quantum system and perform an operation from the incoming system to the outgoing system. And most general quantum operation that one can consider is a so-called quantum instrument. And technically, a quantum instrument is a set of completely positive maps, where each of these completely positive maps is associated to some measurement outcome, and which sum up to some completely positive and trace preserving map. So this is a very general description of a quantum operation, which includes both measurements and, for example, channels or unitary evolutions. And now the point is that one assumes that one has these parties that perform quantum operations, but one does not assume any a priori global causal structure into which these laboratories are embedded. And one asks the question, what are the most general correlations that these parties can establish? It turns out that these correlations are most generally obtained by such a generalized Born rule here. And here one has these MA and ME, these matrices which describe the local operations. So technically speaking, they are the joy representations of the operations that Alice and Bob perform. And one has this object W here, which is an Hermitian operator called the process matrix. And this process matrix describes the environment or the physical resource that relates to operations. So one has this process matrix which receives the output system of Alice and Bob and sends it back to the input system, which then Alice and Bob receive. So the whole situation can be interpreted as a circuit, as a cycle, or this channel corresponding to the process matrix, which goes from the output systems to the input systems, is connected with the local operations. In this abstract top-down approach, the only constraint that one imposes is that a process matrix should generate valid probabilities. And this is equivalent to the process matrix being positive semi-definite in some particular linear subspace of the space of operators over the input and output systems, which guarantees that probabilities sum up to 1. And it has to satisfy some normalization condition. Any process matrix that satisfies these conditions is a valid process matrix in this framework. Now, what kind of situations can we describe in this framework? So, in a way, it is can be understood as a framework that allows to describe both signaling and non-signaling scenarios, like states for the non-signaling case or channels for the signaling case, in a unified framework. So, a process matrix can, for instance, describe a scenario where Alice and Bob perform a measurement on some multipartite state. And in this case, the process matrix would simply be the state, and the generalized Born rule would reduce to the usual Born rule. But the process matrix would also describe such a situation here where Alice performs a preparation and sends the state through a channel to Bob, who performs a measurement. So in that case, we would have signaled from Alice to Bob. But there are also many more general possibilities that this framework permits. Now, what does it mean for a process in this framework to be incompatible with well-defined causal order? So we can look at the most general process matrices that do not allow Bob to signal to Alice. And it turns out that these are equivalent to the standard quantum circuits where Alice acts before Bob. So circuits like this, where Alice receives some part of an entangled state and sends the output through a channel to Bob, who then performs his operation. And similarly, the process matrices that do not allow Alice to signal to Bob are precisely the standard quantum circuits where Bob acts before Alice. And now one can also consider probabilistic mixtures of these two cases. So one can consider that process or some circuit of this kind, this A before B, is performed with some probability, and with 1 minus that probability, the process is B before A is performed. And so this is the most general way in which a process matrix can be compatible with a well-defined causal order. And this property is called causal separability. So process matrix that is causally separable is of this formula. And now the observation that is at the heart of this whole field of research is that there are actually valid process matrices that are not causally separable. So this framework permits for situations where one cannot assign a well-defined causal order to the two operations performed by Alice and Bob. And some causally non-separable process matrices even allow to generate correlations that violate causal inequalities. So similar to well scenarios, one can certify the incompatibility with a well-defined causal order of the situations in a device-independent way. So this is the abstract process matrix framework. And now central question is whether this phenomenon of indefinite causal order has a physical realization or can appear in a physical situation in some way. And it has been speculated on the one hand that such scenarios could appear at the interface of quantum zero and gravity. For instance, there one could have something like a superposition of quantum space-times, which leads to a superposition of causal orders. It can be described by a causally indefinite process. But there are also optical laboratory experiments that have been performed to demonstrate indefinite causal order in the lab. There have been quite a lot of them in recent years. But these experiments have been accompanied by a debate whether they can indeed be considered realizations of processes with indefinite causal order, or some form of simulations of these processes. And as I mentioned in the introduction, one can make a case that these experiments are actual realizations of processes with indefinite causal order. And here the way to make this precise is to note that standard quantum description of these experiments, which is temporal, and description in the abstract process matrix framework are related by a change of subsystems. So let me elaborate on that. So what does it mean to describe a quantum circuit with respect to different choices of subsystems? Let me explain how one can formalize this. So a quantum circuit is an abstract way to describe time evolution in quantum theory. It consists of quantum operations, which are represented by boxes, and which are composed over quantum systems, graphically represented by wires, in some network, which is acyclic for usual quantum circuits, but here we also consider cyclic circuits. And the composition of all operations corresponds to the joint probability associated to the measurement outcomes. Now, how do we change subsystems in quantum theory? We can consider a quantum system, Y, as a Hilbert space associated to it. And this quantum system can be divided into subsystems in different ways. So formally dividing some quantum system into subsystems means choosing a tensor product structure. So, this can be formally defined by isomorphism, which goes from this Hilbert space to some tensor product of Hilbert spaces. And such a choice establishes a notion of locality on the overall Hilbert space and defines the decomposition of the overall system into subsystems. Now, how can we apply this to a whole quantum circuit? The way we do this is the following. So we represent the circuit in an unfolded way like this. So So we consider the tensor product of all operations that occur in the circuit. And this defines quantum operations that acts on the joint Hilbert space of all systems in the circuit. And it is this quantum operation which describes the overall circuit, on which we then change the tensor product structure. So that means we compose it from the left and right with some isomorphism, which defines a new tensor product structure on this overall Hilbert space corresponding to all systems. And this defines an alternative description of the same circuit with respect to another choice of subsystems. So this overall circuit operation is obtained like this, applying this isomorphism J and this global operation that describes the whole circuit. And the systems the new systems that appear here are in general timely localized subsystems. So that means there are some non-trivial subsystems of some joint system, which is composed of systems that are associated to different times. So I consider the Hilbert space of all systems which correspond to different times, and of that composed Hilbert space, one then takes some non-trivial subsystems, which therefore cannot be associated to a definite time and are called timely localized subsystems, first introduced here. So this is the general prescription to change subsystems in a quantum circuit. And let's now see how this can be applied to processes with indefinite causal order. To make the notion precise that these processes can occur within standard physics or standard quantum theory. So an example, maybe the most famous example of a process with indefinite causal order is the so-called quantum switch. The quantum switch is a protocol in which two quantum operations are applied to some target system in a superposition of orders. So here one has UB and UA. So here we consider unitaries, but we can also generalize it to general operations, which are applied to some target system, depending on the value of some control system. So if this control system is in state 0, A is applied before B. And if this control system is in state 1, B is applied before A. And now the interesting case is when one prepares this control system in a superposition state, then indeed one has a superposition of causal orders, which is causally indefinite. And this quantum switch can be described in terms of a process matrix, which there are different versions of it, but you can say that it's four-partite, so one has UA, UB, preparation in the past of the target and control system, and the measurement in the future. And this process matrix describing the quantum switch is indeed causally non-separable. So that is a causally non-separable process, which one finds in the process matrix framework, which is this physical interpretation in terms of the superposition of causal orders. Now this quantum switch has indeed been realized in optical experiments, interferometric experiments that have been performed to realize this causally indefinite process in the laboratory. And such an experiment is schematically shown here. So one can prepare a photon whose polarization acts as the control system, and it is sent through these polarized beam splitters here. So if one has a horizontally polarized photon, it will be transmitted and first go to A and then to B, whereas a vertically polarized photon will be reflected by these polarizing beam splitters and first go to B and then to A. Now, the temporal description of such an experiment would look like that. One has preparation in the past, and then two instances of such controlled operations. So here, at the first time, if the control system is in state 0, UA is applied. If it's in state 1, UB is applied. While here it's vice versa. And now it turns out that indeed for this quantum switch, one can relate this temporal description in terms of some temporal circuit to the description in the abstract process matrix framework by performing a change of subsystems of the type I described. So here, this is shown for a specific example. This is this overall operation that describes this temporal circuit for the quantum switch. And when one composes it with specific isomorphisms, which define new subsystems, one indeed finds something that looks precisely like the cyclic circuit one has in the process matrix framework. So here one has one instance of each Alice's and Bob's operation, preparation, measurement in the past and future, and another operation which corresponds precisely to the process matrix. However, one thing that one needs to note is that one needs to compose over certain systems after doing the subsystem change to arrive at the process matrix description. So, in a way, the cyclic circuit with the new systems can be seen as a fine-grained process matrix perspective. One still needs to compose over certain systems in order to arrive at the process matrix description. So this is how the quantum switch fits into this general picture. And just to mention this, one can do a similar thing for unitary extensions of tripartite processes, which is a particular class of quantum processes with indefinite causal order. So these can also be mapped to a temporal circuit by performing a subsystem change of the kind I described. And what is very interesting is that this class includes processes that can violate causal inequalities. In particular, the so-called Lugano process, which is a specific tripartite process, also a very example that is discussed a lot in the literature, and which has the interesting feature that it is purely classical. So one can indeed violate causal inequalities with classical time localized variables. If you're interested in more details, I recommend you to check out this recent paper we discussed. And here's some outlook on ongoing work. So something that would be very desirable would be if one could transform directly between so-called causal perspectives in the quantum switch. So one can consider different temporal circuits that correspond to the quantum switch or the realized quantum switch, and one can interpret these as different causal perspectives of Alice and Bob. So, for example, you can consider this circuit, which is schematically drawn here, where Alice is localized in time, and Bob's operation is performed either before or after it, depending on the control system. And one can consider the inverse situation where Bob's operation is localized in time, and Alice's operation is delocalized around it. And one may wonder, is there a way to directly transform between these causal perspectives and to find a subsystem transformation that transforms one into the other? Now, it turns out that at least for these temporal realizations of the quantum switch, this is not the case. One can show that there is no subsystem transformation that allows one directly to change from one causal perspective to the other. And in a way, the reason for this is that this fine-grained process matrix picture for the two situations are different. So when one goes from each situation to the process matrix picture, there are some additional systems that appear, and one has to compose over to obtain the process matrix description, like I showed before for the quantum switch. And it turns out that these are not equivalent for the two cases. An open question is whether the framework could be modified to account for this kind of transformations between causal perspectives. And so here is the summary and the conclusion. So the main thing that I showed is that certain processes with indefinite causal order can be mapped to a standard temporal quantum circuit. So there's this subsystem mapping between temporal standard quantum circuits on the one hand, and the abstract process matrix description on the other hand. And in that sense, certain processes with indefinite causal order can be said to have a realization within standard physics, standard quantum theory. Now, I've shown that this works for certain examples or classes of processes. The question is, can it be generalized to other types of processes? Are there processes for which this is not possible? What is the most general class of processes which can be mapped to some temporal circuit in this way? Then one should further develop this notion of transformation between causal perspectives. There's also the question how it is linked to other concepts in the literature, like quantum reference frames, or the idea of a quantum equivalence principle that has been proposed. And when we wonder how this perspective, this way of describing process matrices, what implications it has for quantum information processing with definite causal structures. This is also an interesting question because one can use certain of these processes to perform information processing tasks more efficiently. And when we wonder what implications this perspective has for that. So that's all.
There is a very natural example of where understanding what a subsystem is in time is very difficult, and that is when you have single photon excitations of multiple temporal pulses. So, for example, if you have, say, 5 pulses, classical pulses, you tend to think of each one as a separate mode and treat each one as a subsystem. But there's no compulsion on us to do that. For example, if you just treat those whole 5 pulses as a single temporal mode, with one photon excitation of the whole thing, you don't know which photon the pulse is going to fit the whole 5 pulses at the single time. So I think there are very natural systems in quantum optics where you do have this time delocalization, if I've understood it correctly. So I guess my question is that where one would look for time delocalization, where what you call a single subsystem depends on the modal decomposition of time rather than space.
I'm not sure, but I think that's something more look at potential new realizations of processes with different possibilities. It's definitely an interesting direction.
One more question. Okay, so thank you for a great talk. So I think that in your slides 7 or 8, you have listed some physical realizations of the ICO using some photonic system. I think that this kind of system can be described by computational thermodynamics. But I think in your talk you have mentioned that these are real in the quantum order. So my question is that the ability that the system definition can be described by unitary does not necessarily mean that such kind of experiments are simulations. So I want to know the motivation when there's an ability to write the unitaries in ICA process.
So the idea is, I would say that when this temporal circuit corresponds to the process is performed, then the process actually happens in some well-defined systems. That's the notion of realizations behind this. There are actually some systems that are well-defined subsystems of in the experiment, of which precisely the structure that one describes in the process matrix framework actually happens. That's the sense in which this justifies why this process is these realizations.
We'll all other questions maybe directed to Julian during the coffee break. Let's thank Julian and